Hello, everyone. Thank you very much for attending this talk. I'm Yuli from CUHK. I'm also currently visiting Boston. So today I want to share you some work related to RNA. We know that the bottlenecks for RNA studies is essentially the lack of data. So due to the flexible 3D structures, it's very difficult to determine the 3D structure of RNA. So for the current database, if we remove the redundancy, we will only have around 1,100 RNAs with the 3D structures. And also for a lot of RNAs, we don't know their function. So especially for those non-coding RNAs. But on the other hand, RNAs are very important and they are abundant. So if we use the RNAs as the drug target, probably we will have 100 times more targets than we only consider the proteins as the drug targets. And even if we only consider the non-coding RNA, in the RNA central database, we have around 27 million sequences. So the number of available RNA sequences, if we don't consider it's whether annotated or not, is a lot. So the question will be, is it possible that we take advantage of such huge amount of annotated data to resolve the data scarcity issue and the lack of annotation issue for the RNA studies? And here, we propose such a model which can extract information from those unannotated large amount of data. And it's called the RNA Foundation Model. And we train the model on all the RNA central non-coding RNA sequences. So after removing the redundancy, we have around 23 million sequences. And we use self-supervised learning method to train the model. After the model is trained, the model can output the representations of the input sequences. So we just give the RNA sequence to the model, and then it can output the embedding. And such embeddings can benefit almost all the downstream structure and function prediction applications. So next, I'm going to introduce, first of all, what those embeddings look like, and whether there are some meaning for those embeddings. And secondly, how those embeddings can improve the performance of the downstream application models. Let's first check the embeddings. And in fact, we find the embeddings are meaningful. So here, we visualize the entire RNA universe. And we found that with our embedding, those RNAs belonging to different types can be separated naturally. And we also try to check whether our embedding can be used to infer the evolutionary trend of the non-coding RNAs. And we found that it is consistent with the existing label in the literature. So essentially, RNA Foundation Model can extract the sequence pattern and evolution information. It's not some random representation. Instead, it's some meaningful representation. And then we check whether our embedding or representation of the RNA sequence can improve downstream RNA structure and function prediction tasks. So we first check the secondary structure prediction, which is in fact a very, very well-defined problem. Give the RNA sequence, we predict the base pairing within the sequence. And we found that if we just add one additional layer and with the symbolist fine-tuning, our method based on RNA Foundation Model can already outperform all the previous carefully designed deep learning methods significantly across all the benchmarking datasets. We directly show the cross dataset validation. And we can say for the archive2 dataset, we reach a very, very high performance. For the advanced score is 0.94. And even for this hard dataset from RBP-RNA with low redundancy, we can also outperform the previous methods like U-fold and the spot RNA here by at least 5%. So I noticed that we just use one additional layer without any sophisticated design. And what if we combine RNA Foundation Model with some sophisticated, well-designed model? And in fact, the performance is even more impressive. So we combine RNA-FM with our previous method, the E2E folder. Here we can say, although E2E folder can perform okay on this archive2, it doesn't generalize very well due to the RBP-RNA. But with the help of RNA Foundation Model on this hard data set, the overfitting issue can be resolved very well, and it can outperform the previous methods significantly. Even if compared with the RNA Foundation Model itself, we can also improve the method by about 4% regarding FI score. So here it is to predict the secondary structure. What about we directly predict the 3D structure? So we do such an experiment. So we design an end-to-end model to predict the RNA 3D structure directly based on the RNA Foundation Model embedding. Here, E2E for the 3D will directly predict the RNA 3D structure. We directly optimize against the RNA 3D coordinates. And here we show the performance. So compared to the previous development method, the FAFA2, we can outperform it significantly. On the IMSD, we can improve the method from the average 8 Armstrong to around 3.5 Armstrong. And here we show the performance of our method compared with FAFA2 on each RNA. And we can say we can outperform the method on almost all the RNAs. And the next question is, would our method also improve the further downstream structure prediction applications? So here we use one function prediction task, that is the RNA binding protein and RNA interaction. So this problem is a very important problem. A lot of methods have been developed, such as bind nuclear net and so on. So here we compare our method against those methods. And we found that with the RNA Foundation model embeddings, we can reach similar performance as those methods, which use the real secondary structure profiles from the wet performance. So notice that our method is a purely conditional method. We didn't use any information from the wet performance. However, we can already reach the similar performance with this method with some input from the wet performance. So essentially, to conclude, our method, RNA Foundation Model, by taking advantage of the huge amount of unannotated data, the information extracted from the data can benefit all the downstream tasks, like the structure prediction and the function prediction. Here I want to thank all my collaborators and the team members who contributed to the success of these projects. Without their hard working and talents, we won't be able to make such progress. Finally, thank you very much for your attention. Feel free to contact me if you have any questions.